It's my pleasure today to sort of kick off a panel which Xing Wang will lead. She will introduce the other panelists, so I will not waste her time on that. Xing is a sort of prototype BIDMaP fellow. She started off as a wet lab scientist who didn't even know how to spell AI, and then sort of took a Smith Fellowship for AI for Science, and in 1 year or two became sort of already very fluent, and now is one of our star members. She's working with Dean Toaster and Aditi Krishnapanan at the boundary of now experiments and AI, and is really now core very exactly what BIDMaP could be at this intersection. So thank you so much for organizing that, and please help me welcome her.
Thank you, Christian, for the warm introduction. And I'm Xing Wang. I'm a BIDMaP fellow working on AI for organic synthesis and inorganic nanocrystals. And today it's my pleasure to moderate this session and the panel discussion for my colleagues, Dr. Boyu Xie, and Dr. Mikhail Krumov, and Dr. Ping Po. In today's talk, we will hear three different perspectives on how AI and high throughput methods are reshaping materials discovery, from computational design of carbon nanotubes to high throughput catalyst discovery in the iCAT lab, to generative AI-enabled exploration of reaction networks and phase diagrams. Okay, without further ado, let's get started. Our first speaker is Dr. Boyu Xie. Boyu received his PhD from UC Berkeley with Professor Felix Fischer, and he's in BIDMaP for about 1 year. His talk focuses on computational exploration of low-dimensional carbon nanomaterials using machine learning and high-throughput calculations. Please join me in welcome Boyu.
Thanks, Jane. Hi, everyone. Oh, great, it works. Hi, everyone. My name is Boyu, and as she introduced, I got my PhD here, and I stay here as a BIDMaP fellowship, and doing some cross-boundary research between AI and chemistry. So now I work with Professor Felix Fischer and Professor Aditi Krishnapanan, and the main things we're doing is trying to know how can we actually generate or try to use AI as a very efficient tool help us understand and explore more organic or carbon quantum materials. So over the last 50 years, how our field, which is quantum materials field, or in general the materials field, doing research. We start with some big scientific question, like how can we absorb more light? How can we get a superconductor? And those kind of exciting questions. And we start with some physical theory, like BCS theory, or some chemical structure, like, wow, this is very interesting structure. And then we start to design a molecule or a materials which can have this kind of property or might have this property. We use some theoretical simulation, like DFT, then we do experiments. After that, we use our experiment result to go back to the beginning. How can we redesign everything there? However, this process is very efficient, but very slow. Think about all of the organic, for example, organic OPV things, like organic solar cells. It spent like 30 years, and still it's not in usage. And then we start to focus on a very limited and very fundamental building block, which is nanographene, because this is the origin of all basically organic materials. So those nanographenes are composed by fused phenyl ring or benzene, a little or a lot of hexagonal rings. You can consider all of those nanographenes as an infinite box, and it contains all of them with different properties: electrical, thermal, interstellar. They exist in galaxy everywhere, and magnetic and optical, and all of the properties. And every time when chemists find a new nanographene, it's a good exploration for the whole field. Look at here, research group on this small molecule is around the world, and more than 80,000 papers have been published in the small field. So thinking about all of those small and interesting molecules, we want to know that can we actually change the approach, how we explore those materials. We want to have a conjugated carbon library with all the chemical structures, properties inside, and we can choose structures with interesting properties like their synthesis, electronic, and magnetic optical things inside of one box. And we can just choose one structure we want and then synthesize it. Problem done. However, we know that this is impossible because there are infinite structures. And we tried a lot of generative models, and we cannot generate all of them because the exciting molecule is 1 out of billion, but not an average molecule. So we go back from generative model to a graph theory, which is old and published in 1970s, 1960s. We want to explore how powerful are those old graph theory works. So we try to extract the graph from a chemical molecule as a boundary edge code. Now it's a code. We transform it into a string. Instead of XYZ file, their structural file. Each PH, which is nanographene, has a unique BSA code. So we can use just one number to represent all of them. And then based on only string operation with one desktop, we can generate the whole table for all of the mathematical proven, all of the nanographenes in one night. And look at the number here. There are 0.1 billion structures inside of it. And this cannot be done by just generative model, but generative model, I will mention it in a later stage. Once we have got all of those things, all means mathematical proven thing, we then start out high throughput simulation of all of the molecules from tight binding, mean field hybrid model, those like very physical heaven models to XTB and then to DFT calculation. We have a hierarchical calculation and to high throughput output our properties from geometry optimization to spin density and to orbital energy. And from our 0D nanographene, we got more than 1 billion structures, which is the code inside, and we can go back to XYZ file and then high throughput more than 1 million structure on the binding, and then XTB, DFT, hierarchical thing. And then we can use all of the accurate data that we have chosen and screened by some properties, go to train our model, and then go back to the real structure. Then the next one is, once we have this database, which is clean and efficient, we use it to train our model, we fine tune our foundation model, or we just come up with new architecture that can help us to establish this property and structure relationship. And the last slide is how we end the story. We collaborate with Professor Didi Krishnapurian and her student Eric Chu, and we evaluate everything on their new architecture called Allscape. And we fine tune on the Allscape, which is a foundation model to predict the property of the whole molecule space. And look at the accuracy here. So it not only can give you the correct energy, but it also can give you the correct spin ground state. For example, if we have one molecule, is it singlet, triplet, or quartet? It can predict it very well. Look at it here. So this story is not to show you the details of how can we build a generative model or how can we create a new architecture for machine learning, but it's just a high-level concept for how AI or in general computational method can help us to accelerate our field of science. Okay, thank you.
Our next speaker is Dr. Mikhail Grumuk. Mikhail received his PhD from Cornell University with Professor Hector Bunia and joined BIDMaP last summer. And today he will discuss the development of the Intelligent Catalysis Discovery Laboratory, iCAT. Please welcome Mikhail.
Cool. Yeah, thank you for the kind of introduction. So hello, everyone. My name is Mihail. I work more on the experimental side, so I spend most of my time in the Department of Chemistry, and I work in the laboratory of Professor Peter Yang. And the Yang group does a lot of focused research effort in CO2 conversion. And today I'll tell you about our recent efforts towards discovering new materials for CO2 conversion, which is part of the iCAT laboratory in our group. So first, I'll quickly motivate the need for a CO2 conversion. So CO2 conversion is important for closing the carbon cycle. And that obviously allows the mitigation of atmospheric CO2 and also our reliance on fossil fuels because it's a way to produce fuels and value-added chemicals. Now, it's possible to do CO2 conversion through thermochemical routes. However, that's very generally inefficient because it requires high temperatures and high pressures. And then on the other hand, doing CO2 conversion electrochemically allows us to run reactions at lower temperature, at room temperature, atmospheric pressure, because by electrochemistry allows us to control the thermodynamic driving force for reactions. And that also gives us the ability to have modular systems instead of giant factories. So if we look historically at the field for the development of electrocatalysts for CO2 reduction, a lot of the history starts with the work of Hori back in the late 70s, early 80s, where he systematically investigated different materials for CO2 reduction. And he found that copper is very unique in its ability to make multi-carbon products from CO2 reduction. And so now if we ask ourselves 50 years later, after 50 years of research, what has been achieved? Now, instead of using a bulk rod of copper as a catalyst, we're using nanostructured materials, and we've made advancements in the performance, decrease in the overpotential. However, at the end of the day, what we're still using is just copper. And so, if we look at the progress, right, nanostructuring allows us to increase the density of active sites and lower the overpotential. So catalyst activity is measured relative to a thermodynamic potential, and the closer we can get to the thermodynamic potential, the better our catalyst. And so we've been able to get closer. However, in order to make the next leap forward, really we need new materials. And so to quickly illustrate why that is the case, catalysis essentially relies on the adsorption of intermediates on the surface. And with a complex reaction such as CO2 reduction, where multiple intermediates are involved, it's impossible to have a single active site be optimized to bind multiple intermediates. And so those concepts are known as the Sabatier principle and scaling relation. And so basically that means in order to really push the performance for CO2 reduction, it's really necessary to go to multi-metallic systems, which gives us the ability to design multiple active sites to optimally bind multiple reaction intermediates. And additionally, through the thermodynamics of high-entropy alloys, there's additional benefits such as enhanced structural stability. And the bottom line is this gives us multiple knobs in order to better tune the catalyst performance. However, inherently, this is a combinatorial problem, and so it's a large materials design space to screen, and that really necessitates methods for high-throughput synthesis and also screening the space. As I'm sure you're familiar, across many fields of science, automation is very popular, and catalysis field included. However, oftentimes one of the challenges with automation is it comes at the cost of simplifying the synthetic process. And so there are inherent limitations. So oftentimes when you read the literature, these synthetic processes are based on solution processing, which has certain limitations. And specifically for our purpose, it's very difficult to make high-entropy alloys through solution-based processing because of the variability in the decomposition rate of various precursors. And so to that end, in the Yang group, we've developed this gas phase synthesis strategy in order to synthesize nanoparticles via magnetron sputtering. And so we can have up to 5 different metallic targets in order to make metallic nanoparticles. And the main difference is that the nanoparticle formation is a physical process through vapor phase condensation as opposed to a chemical process. And so that gives us access to a new material space. The other advantage is that sputtering is very quick, so it's possible to synthesize new material in a couple of minutes. Whereas if you're running colloidal reactions, you're typically running maybe 2 or 3 reactions per day. And so it gives us the ability to do a high throughput synthesis of materials. To give you a flavor of what that looks like, this is, for example, the target. We can deposit particles in different substrates, carbon paper for measuring the performance, TM grids for doing structural characterization. And you can see through this means we're able to make monodisperse in small and high quality nanocatalysts with high throughput. Additionally, we also have access to various structures such as core shell or Janus type structures, which again is additional knobs to tune catalytic properties. And so that's on the synthesis side, but of course, high throughput synthesis necessitates a high throughput characterization, and electrochemical characterization is inherently slow conventionally. And so we're using a tool, scanned probe electrochemical microscopy, in order to speed up the electrochemical characterization of materials. The idea here is that we have this pipette, and at the tip of this pipette forms a meniscus, and that meniscus serves as a localized electrochemical cell. And so by scanning the pipette on the different areas of the substrate, we can make localized electrochemical measurements. And so then the idea here is that we can fabricate catalyst arrays via sputtering, and then hop around on different parts of the array in order to measure the catalyst activity. So that part of the process of the development of catalyst arrays is still ongoing work. And so this is not an array of different catalysts. This is a single catalyst deposited on a TM grid. But the purpose here is to show how this tool gives us the ability to spatially resolve electrochemical activity and how it can be applied for catalyst arrays, which we are working on making. And so that's, I'll finish off with a high level overview of how we're using gas phase synthesis and high throughput experimentation in order to screen new material space and apply machine learning in order to efficiently screen the multi-dimensional space and to identify new materials for CO2 conversion. With that, I'd like to thank the Pei-Dong Yang Group and all of you for your attention.
Again, our final speaker is Dr. Ping Tuo. Ping received her PhD from the University of Science and Technology of China, USTC, and in BIDMaP for about 1 year. Her talk focuses on generative approaches for reaction networks and phase diagram prediction. Let's welcome Ping.
Thank you for coming and the kind introduction. And since I'm also part of the iCAT team like Michal, I will focus on the very specific topic of how we use generative AI to advance computational study of catalysis. And since I'm talking about generative AI, I'll give a very brief introduction of the technique. Generative AI trains a machine learning model to map a simple distribution, generally Gaussian, to our target distribution. So it is by design a machine learned free energy mapping. And in chemistry, we know from free energy landscape, we can infer phase diagram by finding out the most stable states at a given condition. And we can infer reaction pathways by finding out the transition path between different states. And so I'll focus on 2 computational challenges we have in catalysis study: reaction network exploration and synthesizability prediction by calculating the phase diagram. Now, reaction network describes the microscopic detail that goes on in a synthesis process or a catalysis process. So the way to build a reaction network is that we start from all the metastable states a system can have, And we figure out all the reactions between two states. And for each reaction, we find out the transition state, which corresponds to a transition barrier. And transition barrier controls the reaction rate of each reaction. Then using the reactions, we can plot a reaction network, which can be very huge and complex for a real system. And here is a workflow. We start from a reactant, find out all the possible products. And for a given reaction, we find out the transition state by like NEB or stream method. Then we do some post-processing to plot the reaction network. And now we can use generative AI to automate and do more efficiently the product enumeration and the transition state sampling. Well, here is a concrete example of our work where we use flow matching, which is one generative modeling technique. Here's a schematic of the flow matching process. We start from a random structure and we feed it into a neural network to predict a velocity field. Then we use the velocity field to transform the random geometry iteratively to our target structure. And for reaction prediction, in order to steer the predicted structure to match specific reactions, we use as input the random interpolant here and also the reactant to steer the target structure to the specific product. And for transition state generation, we're doing the same thing, but we also include the geometry of the product. And we do so by concatenating the message in message passing network of the different geometry. And we feed the concatenated message into a equivalence transformer to predict a velocity field. And here is a metric showing the performance of our model. For product prediction, the metric we use is how many candidates we need to generate to find a product that matches some reference. And as you can see, we can generally find the target product after 3 candidates or no more than 5 candidates. And for transition state prediction, we compare our generated state with the reference, and the dotted line here shows a chemical accuracy. So about 70% of our generated state matches the reference to a chemical accuracy. And the database we use is actually far from perfect. So the valid transition state is actually way higher than that, about 80%. And using these models, we explore the reaction network of gamma kettle hydroperoxide decomposition. And the most straightforward strength of using automated reaction network is that we can reduce the number of quantum chemical steps, which is very expensive, as everyone knows, drastically from over 1,000 to 12. And we identified a novel low barrier pathways here that has a lower barrier than the reported record. Okay, now we'll move on to talk only a little bit, because this is ongoing work, about how we use generative AI to predict synthesizability by calculating the phase diagram. Well, as most of us here must know, using generative AI, we map from a random geometry to a target geometry. But what is less explored is that with the learned mapping, we can do likelihood evaluation of the generated state. And the likelihood or probability is exponentially related to the free energy. And the phase diagram is built by comparing the free energy of different states. So with the trained generative model, we can plot the phase diagram at different conditions of different states. So if we take a step further from here, what we are working on now is scalable or high throughput phase diagram generation to achieve synthesizability aware material design. And here's the 2 topics we talked about today. Thank you.
thank our speakers. Before we go on to the panel discussion, I would like to, any questions you have for our specific speakers here? Okay. So I'll start with a couple of questions and then we'll open the discussion to the audience. So first question is, as we see, especially the open cloud right now, like the AI systems become more powerful and the bottlenecks right now shifts from modeling to data generation, especially the real world data and data infrastructure such as data cleaning, data collecting, data removing. What are the key infrastructure gaps you're facing in your work, and how might we use a robust shared data platform that can support a broader community in this field?
Yeah, I can start now. From a theoretical perspective about data cleaning, it is true that there is a gap between like the dirty data or clean data and everything like that. And what we are facing now, for example, the Carbon Library is the more accurate the more accurate the data will be, and the more calculation time you will spend on it, so more expensive. So it is very tricky or very, very hard to actually choose what is your standard to do the theoretical simulation. If you use only XTB or semi-empirical calculation, you will get a bunch of huge database, but the model you're trained from those data is only semi-empirical level, and you will never get the accurate level. But if you want to do a SSTP level of calculation, which is basically impossible to generate a huge database. So what we are thinking now is, because like Meta and those large companies, they have the almost unified release, they use their extremely huge power on generating higher accuracy of data. And definitely we are in our lab cannot compete with them, right? So what we can do is we use their accurate database, and then we combine with our own unique small database that is great at the same level, but with very specific packets that are not included in their database. And then we can have a very pure and clean, like training set and value set for our model, or even fine tune on their big model. So this is how I think the future will go, and how our labs are gonna survive at the same time with the big companies.
And following that, I can follow up. Do you see a possibility that you have a like wet lab generated data based on your calculations, and how far away your computational data would be from your real world experiment?
That's a very good question. I think for synthesis and experimental data, Michal have more like experience than me. What I can say is theoretical play here is to serve as a role that can help you to screen all of the possibilities that might have in the chemical space, and then it will finally land it on what you measured in the experiment. But it can help you to create a larger chemical space or feature space to help you like gain your knowledge. I think that's how theory is going when you combine theory and experiment. And consider about the clean data on experimental side, and I think we have more things to say.
Yeah, I can comment on data generation in terms of experimental. So for example, the amount of data that I present at subgroup each week is a small fraction of what I actually generate, right? And the problem with having like a database, a universal database that is open access to all researchers that want to develop machine learning models or compare their DFT simulations, is that the cleaning of the data and the data curation takes a lot of effort, right? And so if you have a couple full-time undergrads that are assigned to that, maybe it can happen. But for example, for me leading the project, it's not an efficient use of my time to go through every single experiment that I've done, clean it up, document, this worked, this is what I did, this is why it didn't work, because as you're doing experiments, you know everything that you're doing, and it's all kind of stored in here. But in order to communicate that at a detailed enough level for machine learning to be useful for someone who didn't do the experiment to know what you did, that's a lot of work. So that's, I think, a major challenge.
Do you think if we say document your data cleaning process very well, can we replicate it using like softwares, or do you think it needs grad level students to do the job or undergrad level students?
So once there's the project is advanced enough to where you're kind of very repetitive, that can be more easily automated. But the problem with academic research is it usually isn't very repetitive. Usually you're doing new experiments in order to learn something new. And so that is, I think, challenging in terms of from an academic setting. If you do one experiment, you learn something new, you move on to the next thing. That is kind of research strategy. And unless your group is dedicated to just high throughput, let's just brute force search this space, and then you can automate, then there's not as much academic value for the person doing that data generation.
Yeah, this is fascinating. I'm really curious and sorry for jumping in, but this question of low to medium throughput in where you're very much in a research phase, the higher throughput when you're in a more automated mode is something that is coming up in various scenarios already. Even in academic research, the famous cloud lab that Carnegie Mellon has been trying to build for years, right? I think was an attempt at kind of industrializing university laboratory research processes, and I think they've run into a lot of that type of challenge, right? Can you envision ways in which we could help academic researchers capture, because my fear is that because of these barriers that you're outlining, right, there's a lot of that data that effectively is lost forever, other than in the brain of the one person who was there, right? And I'm not saying that an early career researcher who's in the lab needs to on top of now. I mean, you're already working 80 hours a week. I'm not asking that you work 160 hours a week, right? To write down all of this, that's not practical. But can we imagine ways where the substrates where the data goes have the necessary hooks for you to dump some of that information in other ways, so that it can be learned from, right? Even if it's you learn from it later, others assist you, and where others could be some combination of human machines, right? Is there room to improve how we work? Not that you work more, but that we work with different tool chains and different processes, so that that information can be captured, and that we can actually, in the long run, begin to learn from it, either learn within a lab or learn in the aggregate in a better way.
I definitely do think so, because now that automation is becoming more popular, there's commercial vendors for automated platforms, and then you can start to standardize. But for example, with our tool, which is kind of making it up as we go along, doing that kind of standardization is more challenging. So if you're purchasing commercial tools that have built-in software that record all the parameters, and there's an established workflow that everyone follows, right? There needs to be a universal workflow that's follow, and it's more easily done when we purchase a commercial instrument, like a pipetting robot. It knows what a pipette is programmed to pipette that stuff. I think in those areas it's a little bit easier to just automate. Here's all the data that we get. This is what I pipetted. This is what the XRD was.
Do you think it's Do you think it's possible to say somehow standardize or to record your thinking process in common researchers? Just trying to read.
I wanted to ask the same question, namely, assume that you didn't have to structure anything, okay? So assume you could just, instead of listening to some YouTube music while you do your experiment. You just speak raw text into some microphone as listens. Do you think if you had no responsibility in structuring it, is there still so much in your brain that even sort of the output through your voice is so slow that it would slow you down? Or is it something where it's just, yeah, you force me to put it in a format and put it into a system, and I have to buy and build a machine which does it, but it's in your head. There's so much information in your head that you say it's impossible to get it out if you had this all understanding, I don't know, black box which would just take what you say, and maybe even it doesn't understand anything today, but maybe in 20 years there's an AI which is so good they actually know exactly what you meant? Or do you think there's so much information in your head that just information theoretically getting it out will slow you down?
It depends how intelligent the thing that you're talking to is. For example, if I'm training undergrads or first-year grad students, right, they walk around with me, I talk to them what I'm doing, and they learn it, right? So if you have, a robot that has the intelligence of an undergrad, sure, I can.
Oh, I want it
I can
much more
talk
intelligent. I'm just asking for the future, right? You're just supposed to record it. Think like a doctor, right? So they have to write down, if they have to type all this thing into their codes for the stuff, it takes them forever. But maybe they just dictate. We don't yet have speech recognition, but it's recorded, right? Eventually we have speech recognition, but we don't have the tools to actually put it in a spreadsheet. Then comes ChatGPT, you learn how to put actual information in the speech in a spreadsheet. Now the spreadsheet is still not good enough that Fernando's computer system can really use the data, but maybe future AI can. So I'm wondering, would it be possible for you to future-proof what you have by just, it's almost like I want to freeze my cells in case in 500 years they can make me live forever. Can you freeze your thoughts so they will live forever once you have the intelligence?
Well, I talk with GPT a lot. I find that whatever I talk about, GPT understands way faster than any real person I have talked with. So I think it seems intelligent enough already. And just its interface with all the either your lab or our software is not good enough for it to do what it already knows how to do. What is like a kind of interface, not the brain.
So if we have something like open cloud today, something like robotic and in the lab, and how the robotic to learn what everyone do. Possibly, I think we can record what they say and what they think, and let the platform to write the code by itself and extract the information and thinking processes to train other more powerful or maybe evil AI.
Should have a Roomba with a microphone just following her.
So actually, so Lauren, who's in Gert Cedars Lab, she was telling me just the other day that they do actually all the, they have a robot that transports between the different autonomous stations, and they do it's video recording the entire time that it's doing. And part of the reason they're doing that is so they can record this. And I don't know how they translate from that video to a spreadsheet, but I think it's already there.
Lauren,
No, she had to leave. Unfortunately, she got it down. She had
yeah. Should be turned to the song.
We should actually have, I should have not only thanked you, but also Lauren, the two of them sort of started organizing this. And Lauren had to leave, so she deserves some credit for this beautiful thing.
And maybe for Ping, could you speak a little bit more on your system and how do you have any, say, real world data, or how would you eventually validate your reaction networks or your phase diagram?
For reaction networks, it's not very straightforward to compare it with experimental data. But there are, for the first layer of validation, you have the physical principles. molecules, like your transition state need to sit at exactly. But for certain fields, for example, if your molecules are larger, the transition state is not unique, it can be multiple, so it's even harder. I've talked about this with Sam Lau, and he is working on database in this already. He said the current database is only a proof of concept. It's not used at all. And I actually know a lot of people in this field making database. And but for reaction network, it's particularly hard to control the database. But for stable state prediction, like Venn diagram, it's way easier because you don't have the transition state. So the DMT is more reliable and the oscillation can be shorter. So it depends on the field.
Yeah. And presumably the large complex molecules are for use for medication. Those are the most valuable molecules to compute. Like, how do you see the path from a simple proof of concept but not so useful system to something that really contributes to our development of healthcare, medicine, or organic synthesis for the valuable chemicals? What's the barrier? Like, why it's so hard? Is that the data size, or is that the data cleaning reprocessing?
Well, I think reaction network is more used in either catalysis or combustion with relatively small molecules. For drugs, I think they study the whole transition landscape more instead of the network between discrete states because it's complex. So in each field, they have their own recipe of solutions.
I want to add one side for your last question that why all of the AI model like the reaction pathway cannot give you efficient answer for like drug delivery and society and those things, because there's a concept that is scale different learning, that the data that you learn and everything you learn from this part is for the scale, but not for cross scale like performance. So if we learn the reaction pathway for one molecule, and you know that this molecule might, for example, caffeine, that might help you to prevent get tired or all of the things. However, actually, how the molecule reacts in your body is it collaborates with all of the other molecules together. So it's a multi-scale or macro scale effect instead of one molecule and one quantum pathway there. So that was another problem or open question here. So when AI can learn from the lower level principle, can it be applied to a higher level application that cross those scales? I think that can answer your question if that open question is solved. If that can be done, we can design one molecule and then we can find a quantum pathway and to lead to cure maybe cancer. But you need to find the relation between those different scales.
So you mean we need to somehow learn from the low-dimensional space and somehow across it and apply it in a higher dimensional space?
Yeah, that is one thing, because a lot of macroscope performance or phenomena comes from a lower, like a microscope theory. For example, your enzyme, right? Normally, people simulate enzyme with MD, like molecular dynamic simulation. However, proton tunneling is a very key part for enzyme catalysis. That you have one proton, and which is pure quantum like pathway, but MD cannot tell you that, and which is very important. You can learn. You need to learn not even DFT. You need to learn from CSDT level. You can capture the proton tunneling. But CSDT level can only give you electronic structure for benzene ring, not for enzyme, right? So can you learn from here and then to apply to a higher level system? Then you can fully capture it, which cannot be done by traditional like simulation or traditional pathway. And this is very important and it's open question. We don't know if it can serve like that, but if it can, then it can answer your question. Can we have this? And then to tell me this molecule can cure cancer. It crossed the scale.
That would be great.
That would be great.
Why do you think that is not possible? If I think sort of about how we do computer science, it always is a question of abstraction, right? I sort of work with some very low level system. I try to describe it. I will not describe sort of my programs in sort of processor language. And I don't design internet protocols by worrying about the operating system and the router. And so we do these levels of abstractions. And as scientists, we do the same thing, right? We learn sort of very detailed epsilon delta proofs. Let's say you do math. You learn this very detailed epsilon delta proofs. But eventually you've done enough of the epsilon delta proofs that as a professor, you can actually give your PhD students, say, prove that theorem to me. And you have somehow intuitively abstracted all the logistic details into an abstract language in your head, which abstract all this knowledge at the micro level into a macro level, which is theorem, which says Fermat's last theorem is true or something like that. And so why do you think we can't train machines to do the same?
Well, I'm not saying that we cannot, but it's an open question if how efficient it would be. For example, cross one scale is possible and we can foresee the future now, like you train a DFT level machine learning force field and then apply it to enzyme, which is a traditional MD level thing. But can we actually train things from CCCT and then connect to maybe some quantum phenomenon in our brain? That level cross, and that is the open question. So we already know that it can apply to cross one level, but what about multi-level scale? So that is a question, open question. I think I'm not denying that it will work, but how efficient?
But there is a field of people working on scale simulations. Where extracting data from smaller scale simulations to run.
Yeah.
Yeah, a question I think related to that. Right now we are, especially in our scientific community, we are heavily relying on human-guided decision making. And how do you view the balance between autonomy and human-guided decision making in self-driving platforms over the next 5 years?
I think there's always going to be human guidance, right? That's the area of research. It's kind of like being a PI, where the PI says, you know, let's go and do this area, and then maybe the AI takes the place of the grad students that do the detailed work. There's always going to be a human, I think, on top to kind of drive big picture decisions, because extrapolation is difficult to do with. Right at the core, right? Machine learning is, you know, linear interpolation, doing that extrapolation to find totally different ideas. That's, I think, people will be better at for a long time, for the foreseeable future.
Do you think it's possible that, like right now, our self-driving labs are operating in a safe zone, and you have a really good white box boundaries for them to explore this space? And then do you imagine, like in the next question, we can, if we have something that can really self-driving, and if I give an instruction that please explore other spaces, please do extrapolation and analyze it by yourself, and kind of reinforcement for the entire process, is a way that is it possible the lab can explore different sort of spaces that you never imagined.
It's possible generative AI is possible, right? I mean, there's been examples of generative AI suggesting interesting materials and then people synthesize them, right? Now incorporating that generative AI into an autonomous lab that can do the synthesis instead, automatically instead of a person. That's not too far of an extrapolation. So I think it's possible.
Question, I think consider has done great work.